What if I told you that the world you believe is real might not actually be the way it seems? Right now, the ground beneath you feels solid. Time seems to move steadily forward, and everything around you seems understandable and predictable. But in the world of the universe's tiniest particles, the rules completely change. Electrons can exist in many places at the same time. Two particles can remain mysteriously connected even when they are on opposite sides of the planet. And sometimes, simply observing something can change the outcome itself. It may sound like something from a science fiction story, but the truth is, these are the real rules of quantum physics, a hidden layer of reality that quietly shapes our entire universe. So, tonight, as the world slowly becomes quiet, let us gently drift into that mysterious quantum realm. What if I told you that the world you experience every day might not be exactly the way it appears? Right now, the ground beneath you feels solid. Time seems to move steadily forward. Light travels from place to place, and objects behave in ways that feel predictable and familiar. Our everyday world appears calm and dependable, almost as if the universe follows a clear set of simple instructions. For centuries, scientists believed this was the whole story. They described nature as a giant machine. If you knew the position and speed of every object, you could calculate exactly what would happen next. The future, in theory, could be predicted with perfect accuracy. But as researchers began to explore smaller and smaller scales of reality, something strange began to appear. The rules started to change. At the level of atoms and subatomic particles, the universe behaves in ways that seem almost dreamlike. Instead of moving along clear paths, particles behave more like soft clouds of possibility. Their positions are not fixed points, but regions where they might appear. In this hidden layer of nature, certainty begins to dissolve. Physicists discovered that particles do not always behave like tiny solid balls. Sometimes they spread out like waves moving across water. Other times they appear as single points, arriving suddenly at a specific location. This strange behavior became known as wave-particle duality. Light, which once seemed like a simple beam traveling through space, revealed a dual personality. In some experiments, it behaved like a smooth wave, forming patterns of ripples and interference. In other situations, it arrived as individual packets of energy, called photons, each striking a surface like a tiny particle. The same surprising behavior was later observed with electrons, atoms, and even larger molecules. It was as though the universe itself refused to decide whether these things were waves or particles. Instead, they seemed to exist somewhere in between. To describe this mysterious behavior, scientists developed a new branch of physics known as quantum mechanics. The word quantum refers to the smallest possible units in which certain physical quantities can exist. Energy, for example, does not flow smoothly forever. Instead, it comes in tiny packets, like individual notes in a quiet melody. These packets are unimaginably small, yet they govern the behavior of everything in existence. The atoms in your body, the light reaching your eyes, the chemical reactions that allow life to exist. All of it follows the strange rules of the quantum world. And perhaps the most fascinating part is that we never directly see this hidden layer of reality. The quantum realm is far smaller than the wavelength of visible light, making it impossible for our eyes to observe directly. Yet its influence shapes every moment of the universe.
behind the calm and familiar surface of everyday life lies a deeper framework filled with probability, uncertainty, and subtle connections. It is a place where the future is not completely determined, where possibilities overlap and blend together. And as we slowly continue this quiet journey deeper into the quantum world, we will discover that its mysteries become even more surprising, because the next strange rule of nature reveals something almost impossible. In the quantum universe, energy itself does not flow continuously. Instead, it arrives in tiny, indivisible steps.
As we continue drifting deeper into the quiet world of quantum physics, we begin to notice something unusual about energy itself. In everyday life, energy seems smooth and continuous. When you slowly turn a dimmer switch, a light becomes gradually brighter. When water flows from a faucet, it pours in a steady stream. These experiences make it feel as though energy moves in a perfectly smooth flow, like an endless river. For a long time, scientists believed this was always true. But near the end of the 19th century, a puzzling problem began to challenge that belief. Physicists were studying how heated objects glow. If you heat a piece of metal, it begins to emit light. At first, it glows faintly red. As it becomes hotter, the color shifts toward orange, then yellow, and eventually white. This behavior seemed simple, yet the mathematics used to describe it produced a strange and impossible result. According to classical physics, a hot object should release an infinite amount of energy at high frequencies. In theory, it should shine with limitless brightness. But in reality, this never happens. The prediction was so clearly wrong that physicists called it the ultraviolet catastrophe. For years, no one could explain the discrepancy. Then, in 1900, a German physicist named Max Planck proposed a radical idea. He suggested that energy does not flow smoothly at all. Instead, it is released and absorbed in tiny packets, like individual grains rather than a continuous stream. He called these packets quanta. According to this idea, atoms cannot release just any amount of energy they want. They must emit energy in specific, fixed portions. Imagine climbing a staircase instead of walking up a ramp. You cannot stand halfway between two steps. You must move from one step to the next. Energy behaves in a similar way. This simple yet astonishing proposal solved the mystery of the glowing metal. By allowing energy to exist only in discrete amounts, Planck's theory matched the experimental results perfectly. At first, even Planck himself thought this idea was only a mathematical trick. But within a few years, other scientists began discovering evidence that these energy packets were real. One of the most famous discoveries came from Albert Einstein in 1905. Einstein studied a phenomenon known as the photoelectric effect, where light shining on certain metals can eject electrons from their surface. Classical physics predicted that brighter light should knock out electrons with greater energy. Yet experiments showed something very different. What mattered was not brightness, but the color of the light. Only light above a certain frequency could release electrons, no matter how intense the beam was. Einstein explained this mystery by proposing that light itself comes in tiny packets of energy. Each packet, or photon, carries a specific amount of energy depending on its frequency. If the photon has enough energy, it can knock an electron free. If it does not, nothing happens. This discovery confirmed that energy is fundamentally quantized. It arrives in tiny steps rather than a smooth flow. And this idea opened the door to an entirely new way of understanding the universe. Because once scientists accepted that energy behaves this way, another strange question began to emerge. If light can behave like particles of energy, then perhaps matter itself might also have a hidden wave-like nature. As the idea of quantized energy slowly reshaped physics, scientists began to notice that light behaved in ways that seemed strangely contradictory. Sometimes it moved like a smooth wave spreading through space. Other times, it arrived as tiny packets of energy, each one striking matter like a miniature particle. For many researchers, this dual personality of light was already puzzling enough. Yet an even stranger possibility soon emerged. What if matter itself also possessed this same double nature? In 1924, a young French physicist named Louis de Broglie proposed a bold idea. If waves of light could sometimes act like particles, perhaps particles of matter could sometimes behave like waves. At first, this suggestion sounded almost absurd. After all, everyday objects clearly behave like solid particles. A baseball travels along a predictable path through the air. A grain of sand falls directly to the ground. Nothing about these objects appears wave-like. But de Broglie realized that the wave nature of matter would only become noticeable at extremely tiny scales, where particles move with very small masses and very short wavelengths. Electrons, for example, are unimaginably small and incredibly light. If they truly possessed wave-like properties, those waves might become visible under the right experimental conditions. Within just a few years, scientists found evidence that confirmed his remarkable prediction. In laboratory experiments, beams of electrons were fired toward thin crystals. Instead of simply scattering randomly like tiny bullets, the electrons formed delicate patterns of bright and dark bands on a detector screen. These patterns were unmistakable signatures of waves interfering with each other. It was exactly the same type of pattern produced when water waves overlap in a pond or when light passes through narrow slits. The conclusion was unavoidable. Electrons, which had always been considered particles, could also behave like waves. This discovery changed the way scientists understood matter itself. Instead of imagining electrons as tiny solid objects orbiting an atomic nucleus like planets around a star, physicists began describing them as wave-like probability clouds. These clouds do not represent physical fog surrounding the atom. Instead, they describe where an electron is most likely to appear if someone attempts to measure its position. Most of the time, the electron does not exist at one precise point. Instead, it spreads out across space as a range of possibilities. Only when a measurement occurs does the electron seem to collapse into a single location. This strange behavior raised deep questions about the nature of reality. Does the electron truly exist in many places at once before we observe it? Or does our measurement somehow force the universe to choose one outcome from many possibilities? Physicists still debate the deeper meaning of this phenomenon. Yet the mathematical rules describing these wave-like particles proved extraordinarily accurate. They allowed scientists to predict the behavior of atoms, molecules, and chemical reactions with astonishing precision. In fact, much of modern technology relies on these quantum principles. The electronics inside computers, smartphones, and medical equipment all depend on the wave-like nature of electrons moving through materials. Without this strange dual nature of matter, the technological world we live in today would look very different. But the mysteries of the quantum world do not stop there. Because when scientists began performing even more delicate experiments with particles behaving as waves, they discovered something even more astonishing. A single particle could appear to travel along multiple paths at the same time. As scientists continued exploring the wave-like behavior of particles, they designed experiments to better understand how these tiny objects move through space. One experiment in particular would become one of the most famous in all of physics. It is known as the double-slit experiment. At first glance, the setup is surprisingly simple. Imagine a wall with two very narrow openings cut into it, like two tiny doorways. Behind the wall sits a screen that records where particles land after passing through the slits. If we fire small particles, such as grains of sand, toward the wall, we expect them to behave in a familiar way. Some grains pass through the left slit, others pass through the right, and they land on the screen in two clear clusters directly behind the openings. This is exactly what classical physics predicts. But when scientists performed the same experiment using waves of light, something very different happened. Instead of two clusters, the screen displayed a pattern of bright and dark stripes spreading outward from the slits. These stripes formed because waves passing through both openings overlapped and interfered with one another, creating regions where the waves strengthened each other and regions where they canceled out. This pattern is called an interference pattern, and it is a clear signature of wave behavior. So far, everything seemed understandable. Light behaves like a wave, so it creates wave interference. But the real mystery appeared when researchers repeated the experiment using particles of matter, such as electrons. If electrons were truly tiny particles, they should behave like grains of sand and form two simple clusters on the screen. Yet the result was astonishing. Instead of two clusters, the electrons produced the same interference pattern that waves of light created. This meant the electrons were somehow behaving like waves as they traveled through the slits. To make the experiment even more puzzling, scientists reduced the beam of electrons until they were sending them through the apparatus one at a time. Each electron traveled alone with no other particles nearby. And still, over time, the interference pattern slowly appeared on the screen. It was as though each electron passed through both slits simultaneously and interfered with itself. This idea challenges the way we normally think about motion. In our everyday world, an object must choose one path or another. A car cannot drive down two roads at once. A ball cannot pass through two doors at the same time. But quantum particles seem to behave differently. Before they are measured, they exist in a spread-out wave of possibilities that includes many potential paths. Only when the particle finally arrives at the screen does it appear as a single point. The wave of possibilities collapses into one specific outcome.
Yet the story becomes even stranger. When scientists tried to observe which slit the electron passed through, the interference pattern disappeared. The electron suddenly behaved like an ordinary particle again, choosing only one path. This revealed one of the deepest mysteries of quantum mechanics. The very act of observing a system can change how it behaves. In the quiet world of the quantum realm, simply watching can reshape the outcome. And this discovery would soon lead physicists to an even more unsettling conclusion. Nature itself may limit how much we can ever know about a particle at one time.
The double-slit experiment left scientists with a deeply puzzling question. Why would a particle behave like a wave when it is not being observed, but suddenly act like a solid particle the moment someone tries to measure its path? To explore this mystery, researchers placed tiny detectors near the slits. These devices were designed to observe which opening an electron passed through on its journey to the screen. At first, the expectation seemed simple. The detector would reveal the particle's path while everything else remained the same. But the result was astonishing. The moment the detector was activated, the interference pattern vanished completely. Instead of forming delicate wave-like stripes on the screen, the electrons now produced two simple clusters behind the slits, just like ordinary particles. It was as though the electrons somehow knew they were being observed. Of course, scientists do not believe that particles possess awareness or consciousness. The explanation lies in something more subtle. Any measurement requires an interaction between the particle and the measuring device. Even the gentlest observation disturbs the delicate quantum system. In the microscopic world, these interactions cannot be ignored. The act of measurement changes the conditions under which the particle behaves. Before measurement, the electron exists as a wave of possibilities, spreading across many potential paths at once. But once a detector interacts with it, that wave collapses into a single definite outcome. This idea is known as wave function collapse. The wave function is a mathematical description of all the possible states a quantum particle can occupy. It evolves smoothly over time, describing probabilities rather than certainties. But the moment a measurement occurs, those probabilities suddenly reduce to a single result. One possibility becomes real, while all the others vanish. Why this collapse happens remains one of the deepest puzzles in physics. Some interpretations suggest that measurement forces nature to choose a definite state. Others argue that the wave function never truly collapses at all, and that all possibilities continue to exist in parallel realities. In that view, every measurement simply reveals the branch of reality we happen to experience. These ideas may sound philosophical, yet they arise directly from the mathematics of quantum theory. Despite decades of research, no single interpretation has been universally accepted. What scientists do agree on is that the quantum world does not behave like the predictable mechanical universe once imagined by classical physics. Instead, it operates within a delicate balance of possibilities. Outcomes are not fixed until interactions occur. Even the most precise predictions can only describe probabilities. This realization forced physicists to reconsider one of the oldest assumptions in science, that if we know enough information about a system, we can predict its future perfectly. Quantum mechanics suggests that such perfect knowledge may never be possible, because at the smallest scales of nature, uncertainty is not simply a limitation of our instruments.
it is woven into the structure of reality itself. And this idea would soon be expressed in one of the most famous principles ever discovered in physics, a principle showing that certain properties of a particle can never be known with complete precision at the same time.
As scientists explored the strange behavior of particles in the quantum world, they slowly began to realize that the uncertainty they observed was not simply caused by imperfect instruments. Something deeper was at work. In 1927, a young German physicist named Werner Heisenberg uncovered a principle that would forever change the way we understand knowledge itself. His discovery revealed that certain pairs of properties in the quantum world cannot both be known with perfect precision at the same time. This idea became known as the Heisenberg uncertainty principle. At first, the concept may sound technical, but its meaning is surprisingly simple. Imagine trying to measure the exact position of a tiny particle, such as an electron. To see it clearly, you must shine light on it, but light itself carries energy and momentum. When a photon of light strikes the electron, it slightly disturbs the particle's motion. The more precisely you measure the electron's position, the more you disturb its motion. As a result, the electron's momentum becomes uncertain. If you attempt the opposite approach and measure the electron's momentum very carefully, you must allow its position to remain more spread out and uncertain. In other words, the more precisely you know where a particle is, the less precisely you can know how fast it is moving. And the more precisely you know its motion, the less certain its position becomes. This is not simply a limitation of our technology. Even with perfect instruments, nature itself prevents both quantities from being known simultaneously with infinite accuracy. Uncertainty is built into the very structure of the quantum world. This idea shocked many physicists when it was first introduced. For centuries, science had been guided by the belief that if we could measure everything precisely enough, we could predict the future with certainty. The universe was thought to behave like a perfectly engineered clock. But Heisenberg's discovery suggested that the universe is not a clock at all. Instead, it is more like a gentle cloud of probabilities, where outcomes can only be predicted in terms of likelihood rather than certainty. Particles do not travel along sharply defined paths waiting to be measured. Instead, their properties exist within ranges of possibility until an interaction occurs. This shift in thinking was deeply unsettling for some scientists. Einstein, for example, struggled with the idea that nature might contain fundamental randomness. He famously remarked that he could not believe that God plays dice with the universe. Yet experiment after experiment has confirmed the predictions of quantum mechanics with remarkable accuracy. The uncertainty principle does not mean that the universe is chaotic or without structure. The laws of quantum mechanics are incredibly precise. They allow scientists to calculate probabilities with extraordinary detail. What has changed is our understanding of certainty. In the quantum world, the future is not fixed in advance. Instead, it unfolds from a delicate balance of possibilities. And within that balance lies another extraordinary phenomenon. Because sometimes a single quantum particle can exist in several different states at the same time. As the implications of quantum uncertainty slowly became clearer, physicists encountered another concept that seemed even more astonishing. In the microscopic world, particles do not always exist in just one state at a time. Instead, they can exist in several possible states simultaneously. This remarkable property is known as quantum superposition. To understand the idea, imagine a simple object, such as a coin. When a coin is tossed into the air, it spins rapidly between heads and tails. Yet, at any single moment, the coin still has a definite orientation. If you could freeze time, the coin would be either heads or tails. In the everyday world, objects always possess one specific state. But quantum particles behave differently. An electron, for example, can spin in one direction or the opposite direction. In classical physics, it would have to be one or the other. Yet in quantum mechanics, the electron can exist in a superposition of both possibilities at once. It is not simply switching back and forth between them. Instead, it exists in a delicate combination of both states simultaneously. This superposition is described mathematically by a wave function that includes all possible outcomes. The particle remains in this blended state until something interacts with it. When a measurement occurs, the superposition collapses and only one outcome becomes visible. Before that moment, however, all the possibilities coexist. At first glance, this idea feels impossible. How can something be in multiple states at once? Yet countless experiments have confirmed this behavior in the quantum world. Electrons, photons, and atoms all demonstrate superposition under carefully controlled conditions. Even molecules composed of hundreds of atoms have been placed into superpositions during laboratory experiments. The reason we do not observe superposition in everyday objects is that large systems interact constantly with their surroundings. These interactions quickly destroy delicate quantum states through a process called decoherence. As a result, the strange behavior of superposition remains hidden at microscopic scales. But the principle itself has profound implications. Because if particles can exist in multiple states simultaneously, then calculations involving those states can also occur simultaneously. This idea lies at the heart of quantum computing. Unlike classical computers, which process information using bits that represent either 0 or 1, quantum computers use quantum bits, or qubits. A qubit can exist as 0, 1, or a superposition of both at the same time. This allows a quantum computer to explore many possible solutions to a problem simultaneously, rather than checking each one individually. In theory, this could allow quantum computers to solve certain complex problems far more efficiently than any classical machine. Researchers around the world are working to harness this strange property of nature, building experimental quantum processors that operate at extremely cold temperatures to preserve delicate quantum states. While practical quantum computers are still developing, the principle behind them reveals something profound about reality. At the smallest scales of existence, nature does not limit itself to single outcomes. Instead, it explores many possibilities at once. And this leads to an even deeper realization about the quantum world. Because in this strange realm, reality itself is described not by certainties, but by probabilities. As the concept of superposition became better understood, physicists began to see that the quantum world operates according to a very different philosophy than the everyday universe we experience. In our normal lives, events appear to follow clear and definite outcomes. If you roll a ball across a table, its path can be predicted. If you drop a stone, it will fall toward the ground with dependable certainty. Classical physics was built upon this sense of determinism. If you know the position and speed of an object, you can calculate where it will be in the future. But quantum mechanics tells a very different story. At the smallest scales of nature, particles do not carry definite answers about where they are or what they will do next. Instead, they carry a range of possibilities. These possibilities are described by the particle's wave function. The wave function is not a physical object you can touch or see. It is a mathematical description that tells us the probability of finding a particle in different places or states when a measurement is made. Imagine standing on the shore of a calm lake and watching gentle ripples spread across the water. The ripples do not mark a single point where the water must move. Instead, they describe a pattern of motion spreading over an area. In a similar way, the wave function spreads the possible locations of a particle across space. Where the wave is strongest, the particle is more likely to appear. Where the wave is weaker, the particle is less likely to be found. But until a measurement takes place, the particle itself is not located at any one point. It exists within that spread of possibilities. This idea can feel deeply counterintuitive because our everyday experiences train us to expect certainty. Yet experiments repeatedly confirm that quantum systems truly behave this way. Even when scientists prepare identical particles under identical conditions, the results of measurements can still vary. One particle might appear in one location, while the next appears somewhere slightly different. The wave function can predict the statistical pattern of these outcomes with extraordinary accuracy, but it cannot determine the result of any single measurement in advance. Each outcome emerges from the cloud of possibilities. This probabilistic nature of reality troubled many early physicists. Albert Einstein was especially uneasy with the idea that the universe might operate through fundamental randomness. He believed that hidden variables might exist, unknown factors that determine the precise behavior of particles behind the scenes. But decades of experiments have shown that quantum mechanics accurately describes the results we observe. Nature itself appears to operate through probabilities at its most fundamental level. This does not mean the universe lacks order. On the contrary, the equations of quantum mechanics are among the most precise and successful theories ever developed in science. They allow us to predict the behavior of atoms, molecules, and materials with astonishing precision. What they reveal is simply that certainty is not always part of the universe's design. Instead, reality emerges from a tapestry of probabilities. And hidden within that tapestry lies another mystery, a question that has puzzled scientists for nearly a century. What exactly happens when those probabilities collapse into a single outcome?
As we continue exploring the quiet landscape of quantum physics, we arrive at one of the most mysterious moments in all of science. It is the instant when many possibilities suddenly become one single reality. In the quantum world, particles are described by wave functions that spread out across many possible states. An electron may have several possible positions. A photon may travel along several potential paths. These possibilities coexist together within the gentle mathematics of quantum theory. Yet, when a measurement occurs, something remarkable happens. All those possibilities appear to collapse into one definite outcome. Physicists call this process wave function collapse. Before the measurement, the particle exists in a superposition of possibilities. After the measurement, it appears in one specific state. The wave of probability disappears, leaving behind a single result. But what exactly causes this collapse? This question has puzzled scientists for decades. In the early days of quantum theory, some physicists suggested that the act of measurement itself forces the system to choose an outcome. When a quantum particle interacts with a measuring device, the delicate superposition of states can no longer survive. The particle becomes locked into one observable state. Yet this explanation raises deeper questions. What counts as a measurement? Does it require a conscious observer, or is any interaction with the environment enough to collapse the wave function? Different interpretations of quantum mechanics offer different answers. One interpretation, known as the Copenhagen interpretation, suggests that quantum systems remain in superposition until a measurement occurs. The act of observation forces nature to select one of the possible outcomes. Another interpretation proposes something even extraordinary. According to the many worlds interpretation, the wave function never truly collapses at all. Instead, every possible outcome continues to exist, but in separate branches of reality. Each measurement splits the universe into multiple versions, with each branch containing one of the possible results. In this view, countless parallel histories unfold simultaneously, even though we only experience one of them. There are also other interpretations that attempt to explain the collapse of the wave function through hidden mechanisms or physical processes that have not yet been fully discovered. Despite many decades of debate, no single interpretation has been universally accepted. What makes this mystery so fascinating is that all of these interpretations produce the same observable predictions. The mathematics of quantum mechanics works perfectly regardless of which explanation we choose to believe. Experiments confirm the accuracy of the equations again and again. Yet the deeper meaning behind those equations remains open to interpretation. It is as if nature reveals the rules of the game, but keeps the reason for those rules hidden behind a veil. Perhaps future discoveries will bring greater clarity. Or perhaps the universe simply operates in ways that stretch beyond the limits of human intuition. Either way, the strange moment when possibilities become reality remains one of the most beautiful puzzles in science. And this puzzle becomes even more intriguing when we imagine applying quantum ideas to something larger. Because one famous thought experiment asks a startling question. What would happen if an ordinary object existed in a superposition of life and death at the same time?
As physicists struggled to understand the strange implications of quantum superposition, one scientist proposed a thought experiment that would become one of the most famous illustrations of quantum theory. In 1935, Austrian physicist Erwin Schrödinger imagined a simple but unsettling scenario. Picture a sealed box placed on a table. Inside the box is a living cat. Alongside the cat sits a small device connected to a tiny radioactive atom. The device is designed in a very particular way. If the atom decays, a detector triggers a hammer that breaks a vial of poison. If the atom does not decay, the vial remains intact and the cat stays alive. The key detail is that radioactive decay is a quantum process. According to quantum mechanics, until a measurement occurs, the atom exists in a superposition of two states, decayed and not decayed. If the atom is both states at once, then the device connected to it must also exist in two states. The vial is both broken and unbroken. And if that is true, the cat itself must also exist in a superposition, alive and dead at the same time. This strange scenario was not meant to suggest that cats truly live in such a state. Schrödinger actually proposed the thought experiment to highlight how bizarre quantum ideas become when applied to everyday objects. In the microscopic world of atoms and particles, superposition is well established. Experiments repeatedly confirm that quantum systems can exist in multiple states simultaneously. But when we move into the larger world of ordinary objects, we never see such behavior.
A cat is always either alive or dead, never both. So where does the boundary between the quantum world and the classical world appear? This question has fascinated physicists for decades. One explanation involves a process known as decoherence. In the real world, objects constantly interact with their surroundings. Light, air molecules, and thermal vibrations continuously exchange energy with matter. These interactions quickly destroy delicate quantum superpositions. The larger the system becomes, the more interactions occur, and the faster the superposition collapses into a single state. In the case of Schrödinger's cat, the countless interactions between the cat and its environment would eliminate any quantum superposition almost instantly. As a result, we only ever observe one outcome. The cat is either alive or dead. Yet the thought experiment remains powerful because it forces us to confront the strange logic of quantum mechanics. If the equations describing particles are correct, then superposition must be a real property of nature. Somewhere between the microscopic world of atoms and the macroscopic world of everyday objects, the delicate quantum behavior fades away. Understanding exactly how and where this transition occurs is still an active area of research. Modern experiments have even placed tiny mechanical devices and clusters of atoms into quantum superpositions, slowly pushing the boundary between the quantum and classical worlds. Each new experiment reminds us that reality may be far stranger than our everyday experiences suggest. And the deeper we look into the quantum realm, the more surprising connections we discover. Because sometimes two particles can become linked in such a profound way that their states can no longer be described independently. They become part of a single shared quantum system. As physicists continued uncovering the strange behaviors of the quantum world, they encountered a phenomenon so unusual that it challenged one of our deepest assumptions about reality. This phenomenon is known as quantum entanglement. At first glance, entanglement sounds simple. When two particles interact in certain ways, their quantum properties can become linked together. After this interaction, the particles are no longer completely independent systems. Instead, they behave as parts of a single shared quantum state. What makes this connection extraordinary is that it can persist even when the particles are separated by enormous distances. Imagine two particles created together in a laboratory. At the moment they interact, their properties become intertwined through the rules of quantum mechanics. If scientists then send these particles far apart from each other, the connection between them remains. Now, suppose we measure a property of one particle. Instantly, the corresponding property of the other particle becomes determined as well. This happens even if the two particles are located on opposite sides of the planet. To understand why this is so surprising, it helps to think about how we normally expect the world to behave. In everyday life, information travels from place to place through signals. A message must move through space, carried by sound waves, light, or some other form of transmission. Nothing can travel faster than the speed of light, but entangled particles seem to coordinate their properties instantly without any visible signal passing between them. It is almost as though the two particles remain connected by an invisible thread, regardless of the distance separating them. Of course, physicists do not believe that information is secretly traveling faster than light. Instead, the explanation lies in the nature of the shared quantum state. Before measurement, the two particles do not possess independent properties. Their states are described together as one combined system.
Only when a measurement occurs do the individual properties become defined. When we measure one particle, we are not sending a message to the other. We are simply revealing information about the shared quantum state that already existed between them. Even so, this phenomenon remains deeply counterintuitive. It suggests that the universe may be more interconnected than our everyday experiences imply. In the classical world, objects appear separate and independent. A stone on one side of the Earth has no immediate influence on another stone thousands of kilometers away. But the quantum world operates according to different principles. Particles can share relationships that stretch across space itself. Over the years, scientists have created entangled pairs of photons, electrons, and atoms in laboratories around the world. They have tested these systems over increasingly large distances, confirming that predictions of quantum mechanics hold true. Each experiment strengthens the evidence that entanglement is not a theoretical curiosity. It is a genuine feature of nature. And yet, when this idea was first proposed, it made even the greatest scientists uneasy. One of the most famous critics of quantum entanglement was Albert Einstein. He believed that something about the theory must still be incomplete. In fact, he gave this mysterious connection a name that would become legendary in physics. He called it spooky action at a distance.
When the idea of quantum entanglement first appeared, many physicists found it fascinating. But one of the greatest scientific minds in history found it deeply troubling: Einstein. Einstein had helped shape the early development of quantum theory. His explanation of the photoelectric effect even earned him the Nobel Prize. Yet, as the theory continued to evolve, he became increasingly uncomfortable with its strange implications. In particular, the idea of entanglement seemed to challenge one of the central principles of Einstein's own theory of relativity. According to relativity, nothing in the universe can travel faster than the speed of light. This limit protects the structure of cause and effect. A signal must move through space before it can influence something far away. But entanglement appeared to ignore this rule. If two particles were entangled and separated by a great distance, measuring one particle seemed to instantly determine the state of the other. The change happened immediately, regardless of the distance between them. To Einstein, this seemed impossible. He believed that there must be some hidden mechanism behind the scenes. Perhaps the particles carried secret instructions that predetermined how they would behave when measured. In 1935, Einstein worked with two colleagues, Boris Podolsky and Nathan Rosen, to present a famous argument questioning the completeness of quantum mechanics. Their proposal became known as the EPR paradox, named after the initials of their last names. The idea was meant to show that if quantum mechanics were correct, then it would imply one of two disturbing possibilities. Either information was somehow traveling faster than the light of space between distant particles, or particles did not possess definite properties until they were measured. Both possibilities seemed unacceptable to Einstein. He preferred to believe that hidden variables existed within the particles themselves. These hidden factors would determine the outcomes of measurements in advance, preserving the idea that the universe operates through clear and predictable laws. For many years, the question remained unresolved. Quantum mechanics continued to produce correct predictions for experiments, yet Einstein's concerns lingered in the minds of many scientists. Could hidden variables exist, quietly guiding the behavior of particles behind the scenes?
Or was the universe truly as strange and interconnected as quantum theory suggested? For decades, this debate remained largely philosophical. Scientists did not yet have the experimental tools needed to test the competing ideas directly. But that situation began to change in the 1960s. A physicist named John Bell discovered a way to turn this philosophical argument into a testable scientific experiment. Bell developed a mathematical inequality that allowed researchers to compare the predictions of quantum mechanics with the predictions of hidden variables theories. If Einstein's idea about hidden variables were correct, the results of certain measurements would follow specific limits. But if quantum entanglement truly worked the way quantum theory predicted, those limits could be violated. Bell's discovery transformed the debate from a matter of opinion into a question that experiments could answer. And when scientists finally performed those experiments, the results would reveal something remarkable about the nature of reality. The universe, it seemed, did not behave according to the comfortable expectations of classical physics. When John Bell introduced his remarkable theorem in 1964, he gave physicists something they had been waiting for: a way to test whether Einstein's hidden variables truly existed. For decades, the debate about quantum entanglement remained mostly theoretical. Some scientists believed that deeper hidden rules must guide the behavior of particles, while others trusted the strange predictions of quantum mechanics. Bell's work changed everything. He showed that if hidden variables controlled the outcomes of measurements, then the correlations between entangled particles would follow strict mathematical limits. These limits became known as Bell's inequalities. Quantum mechanics, however, predicted something very different. According to quantum theory, entangled particles could produce correlations stronger than those limits allowed. This meant that carefully designed experiments could reveal which description of nature was correct. If the results followed Bell's inequalities, Einstein's idea of hidden variables might still be valid. But if the results violated those inequalities, then the universe truly behaved according to the strange principles of quantum entanglement. For several years, the experiments required to test Bell's theorem remained difficult to perform. Measuring delicate quantum systems without disturbing them too much posed a serious challenge. But by the 1970s and 1980s, scientists began developing the technology needed to test Bell's predictions. One of the most famous experiments was conducted by physicist Alain Aspect and his colleagues in France during the early 1980s. They created pairs of entangled photons and sent them toward detectors positioned at different angles. By measuring the polarization of each photon, the researchers could compare the correlations predicted by hidden variable theories and quantum mechanics. The results were striking. Again and again, the experiments violated Bell's inequalities exactly as quantum mechanics predicted. The correlations between entangled particles were stronger than any hidden variable explanation could allow. Over the following decades, scientists repeated these tests with increasing precision. They improved detectors, eliminated potential loopholes, and extended the distances between entangled particles. Some experiments sent entangled photons through optical fibers stretching across entire cities. Others sent entangled particles between ground stations and satellites orbiting Earth. In every case, the results matched the predictions of quantum mechanics. The universe truly appeared to support the strange connections described by entanglement. This did not mean that information was secretly traveling faster than light. Instead, it suggested something more subtle.
the properties of entangled particles simply do not exist independently until they are measured. Their states are defined together as part of a shared quantum system. Even when the particles are separated by great distances, their connection remains encoded in that shared description. For many physicists, these experiments marked one of the most profound discoveries in modern science. They revealed that the universe cannot be fully explained by classical ideas of local cause and effect. Instead, reality appears to contain deep relationships that stretch across space itself. And once scientists accepted the reality of entanglement, they began to wonder whether this strange phenomenon could be used for something practical. Because if particles can share information across vast distances in such a subtle way, perhaps that connection could become the foundation for entirely new technologies. One of those possibilities would soon be called quantum teleportation.
As scientists gradually accepted the reality of quantum entanglement, a fascinating question began to emerge. If two particles can share a deeply connected state across large distances, could that connection be used to transfer information from one place to another in a completely new way? The answer turned out to be yes, though not in the way science fiction often imagines. The process is known as quantum teleportation. Unlike the teleportation seen in movies, quantum teleportation does not move physical objects through space. No person, chair, or spacecraft suddenly disappears and reappears somewhere else. Instead, quantum teleportation transfers something far more subtle, the quantum state of a particle. A quantum state contains the full description of a particle's properties. It includes information about its position, spin, polarization, and other characteristics that define how the particle behaves. In ordinary communication, information is copied and transmitted through signals such as radio waves or electrical pulses. But the quantum world follows a special rule known as the no-cloning theorem. This rule states that an unknown quantum state cannot be perfectly copied. So, if a quantum state cannot simply be duplicated, how can it be transferred? The answer involves entanglement. Imagine two scientists, one in a laboratory on Earth and another far away at a distant station. Before the experiment begins, they create a pair of entangled particles. One particle stays with the first scientist, while the other is sent to the distant location. Because the particles are entangled, they share a single quantum connection. Now, suppose the scientist on Earth wants to teleport the quantum state of a third particle to the distant station. She performs a special measurement involving her two particles, the original particle and the entangled one. This measurement destroys the original quantum state, but it also sends a small piece of classical information to the distant station. When the distant scientist receives that information, he applies a specific transformation to his entangled particle. Remarkably, the particle at the distant station now takes on the exact quantum state that the original particle had before the measurement. The state has effectively moved from one location to another. The original state no longer exists at its starting point, and the distant particle now carries the complete quantum information. In this sense, the quantum state has been teleported. This process has already been demonstrated in laboratories around the world using photons, atoms, and trapped ions. Scientists have even performed quantum teleportation between ground stations and satellites orbiting Earth.
While these experiments involve extremely tiny systems, they represent an important step toward future technologies. Quantum teleportation could become a key component of quantum communication networks, sometimes called the quantum internet. Such networks might allow information to be transmitted with extraordinary security, protected by the fundamental laws of physics. Any attempt to intercept the information would disturb the quantum states involved, immediately revealing the presence of an eavesdropper. In this way, one of the strangest features of the quantum world may eventually become a practical tool. Yet, quantum teleportation is only one example of how entanglement might transform technology. Because the same principles also open the door to a new kind of computing power, one that operates according to the mysterious rules of the quantum universe itself.
As scientists explored the strange rules of quantum mechanics, they began to realize that these unusual behaviors might do more than simply describe nature. They might also provide new ways to process information. This idea gave rise to the concept of quantum computing. Traditional computers operate using bits, the basic units of digital information. A bit can exist in only one of two states, 0 or 1. Every calculation performed by a classical computer ultimately depends on combinations of these simple binary states. Quantum computers, however, use a different kind of information unit known as a qubit or quantum bit. Unlike an ordinary bit, a qubit can exist in a superposition of states. This means a qubit can represent 0, 1, or a combination of both at the same time. Instead of choosing between two possibilities, it holds a range of possibilities simultaneously. This property alone allows quantum systems to explore multiple potential solutions at once. But the power of quantum computing grows even greater when superposition combines with another quantum phenomenon we have already encountered: entanglement. When qubits become entangled, their states become linked together. A change in one qubit can influence the others, creating coordinated patterns of information that classical systems cannot easily replicate. In a quantum computer, many entangled qubits can work together as a unified system. Instead of performing calculations step by step, the machine explores many possible computational paths at the same time. For certain types of problems, this approach can offer extraordinary advantages. One example involves factoring very large numbers into their prime components. Classical computers can perform this task, but it becomes extremely difficult as the numbers grow larger. Quantum algorithms, however, could solve such problems far more efficiently. This possibility has major implications for modern cryptography. Many encryption systems rely on the assumption that factoring large numbers is computationally difficult. If large-scale quantum computers become practical, new forms of secure communication may be required. Quantum computers could also transform fields such as chemistry, materials science, and drug discovery. Simulating the behavior of molecules is extremely challenging for classical computers because the number of possible quantum interactions grows enormously with each additional particle. But quantum computers operate according to the same quantum rules that govern molecules themselves. This makes them uniquely suited to simulate complex atomic systems. Scientists hope that quantum simulations may eventually lead to the discovery of new medicines, more efficient energy systems, and advanced materials with remarkable properties.
Despite this promise, building a fully practical quantum computer remains an enormous challenge. Quantum states are extremely delicate. Interactions with the surrounding environment can quickly destroy superpositions and entanglement, a process known as decoherence. To preserve quantum behavior, many experimental quantum processors must operate at temperatures close to absolute zero. Even so, researchers around the world are steadily improving the technology. New designs, error correction methods, and materials are gradually bringing quantum computing closer to reality. Yet the deeper lesson of this research extends beyond technology. It reminds us that the strange principles of the quantum world are not just theoretical curiosities. They are part of the hidden structure of reality itself. And as scientists continue exploring that structure, they have begun to uncover something even more surprising about the nature of empty space.
As we continue drifting deeper into the strange landscape of quantum physics, we arrive at a place that appears, at first, completely empty. Empty space. In everyday thinking, a vacuum is simply nothingness. If we remove all air, all dust, and all particles from a region, what remains seems like pure emptiness. For centuries, scientists imagined that the vacuum was exactly that, an absolute void where nothing at all happens. But quantum physics reveals something far more mysterious. According to modern theory, even the emptiest vacuum is not truly empty. Instead, it is filled with restless activity at the smallest scales of nature. This surprising idea emerges from the same uncertainty principle we explored earlier. In the quantum world, certain pairs of physical quantities cannot both remain perfectly fixed. One of these pairs involves energy and time. The uncertainty principle allows tiny fluctuations of energy to appear for extremely brief moments as long as they vanish quickly enough. Because of this rule, empty space constantly experiences tiny bursts of energy that flicker in and out of existence. These fleeting disturbances give rise to what physicists call virtual particles. Virtual particles are not particles in the usual sense. They cannot be directly observed or captured. Instead, they are temporary excitations of quantum fields that briefly appear before disappearing again. They exist for such short intervals that they leave behind only subtle effects. Yet, those effects can be measured. One of the most famous examples is known as the Casimir effect. When two perfectly smooth metal plates are placed extremely close together in a vacuum, they experience a tiny attractive force pulling them toward each other. No classical explanation accounts for this force, but quantum theory predicts that the fluctuating energy of the vacuum changes slightly between the plates, creating a pressure difference that pushes them together. The effect is incredibly small, yet experiments have confirmed it with remarkable precision. Another example of vacuum fluctuations appears in particle physics experiments, where these fleeting disturbances influence the behavior of real particles. Even the properties of atoms are subtly shaped by the constant background activity of the quantum vacuum. In a sense, the universe is never truly still. Even when space appears perfectly empty, invisible energy continues to ripple beneath the surface. Some physicists have suggested that the entire universe may have emerged from a quantum fluctuation in an early vacuum state, a tiny ripple of energy that expanded into the vast cosmos we observe today. If that idea is true, then everything we know may have begun with the quiet flicker of energy in what once seemed like nothing at all. And as we continue exploring the quantum world, we begin to discover that these invisible fields influence the behavior of every particle in existence. As physicists studied the strange activity of the quantum vacuum, they began to realize that particles themselves might not be the most fundamental ingredients of the universe. Instead, something even deeper may exist beneath them. This idea led to the development of quantum field theory, one of the most successful frameworks in modern physics. According to this view, the universe is filled with invisible fields that extend throughout all of space. These fields exist everywhere, even in regions where no particles are present. Particles are simply tiny excitations within these fields. To imagine this, picture a calm lake stretching out in every direction. The surface of the water represents a field. When a ripple moves across the surface, we see a small wave traveling through the lake. In quantum field theory, a particle is similar to that ripple. An electron is a vibration in the electron field. A photon is a vibration in the electromagnetic field. Other particles arise as vibrations within their own corresponding fields. These fields overlap throughout space like layers of an invisible fabric. Wherever energy disturbs one of these fields, a particle appears. When the disturbance fades, the particle disappears again. This picture helps explain many puzzling features of quantum physics. For example, it explains why identical particles are truly identical. Every electron in the universe behaves in exactly the same way because each one is simply a vibration in the same underlying electron field. They are not separate objects created independently. They are repeating patterns within a single universal field. Quantum field theory also explains how particles can be created and destroyed. In high-energy experiments, scientists sometimes observe particles suddenly appearing during collisions between other particles. In these events, energy is transferred into the underlying fields, causing new excitations to form. The new particles emerge briefly before interacting and transforming into other particles again. The fields themselves remain, quietly filling all of space. One of the most famous discoveries connected to these fields is the Higgs field. According to modern theory, the Higgs field exists everywhere in the universe. Particles moving through this field interact with it in different ways, and these interactions give particles their mass. Some particles interact strongly with the Higgs field and become heavy. Others interact weakly and remain very light. In 2012, scientists at the Large Hadron Collider finally confirmed the existence of the Higgs boson, the particle associated with this field. The discovery provided powerful evidence that the universe truly operates according to the principles of quantum fields. When viewed through this lens, reality begins to look very different from the solid world we experience. Instead of a universe made of tiny individual objects, we see a vast network of invisible fields continuously vibrating and interacting. Particles become brief patterns of motion within those deeper layers. Everything, from the atoms in your body to the distant stars in the sky, emerges from the activity of these underlying fields. The solid objects around us are not truly solid at all. They are stable arrangements of energy moving within an invisible framework that fills all space.
And when scientists look even closer at the behavior of these quantum fields, they discover that some particles display an especially fascinating pattern of motion. One of the most familiar examples is the electron, whose presence spreads through space in a delicate cloud of probability.
As our journey through the quantum world continues, we return to one of the most familiar particles in nature, the electron. Electrons are everywhere. They flow through the wires that power our homes, shape the chemistry of atoms, and allow molecules to form the complex structures required for life. Yet despite their importance, electrons behave in ways that challenge our everyday intuition. In classical physics, we might imagine an electron as a tiny solid particle orbiting the nucleus of an atom in a neat circular path, much like a planet circling the sun. Early models of the atom even used this planetary picture, but quantum mechanics revealed a very different reality. Electrons do not travel along precise orbits. Instead, they exist in regions of probability surrounding the atomic nucleus. These regions are often called electron clouds. The cloud does not represent a physical mist or fog. Rather, it describes the likelihood of finding the electron in different locations when a measurement is made. In some areas of the cloud, the probability is high, meaning the electron is more likely to appear there. In other areas, the probability is very low. The shape of these probability clouds depends on the quantum state of the electron. Some electron clouds form simple spherical shapes around the nucleus. Others stretch into elongated or more complex patterns that resemble petals or rings. These patterns are known as atomic orbitals, and they determine how atoms interact with one another to form molecules. The structure of every chemical substance, from water to DNA, arises from the arrangement of these quantum orbitals. Even so, the electron is not the only particles with surprising properties. Light itself, carried by particles known as photons, also behaves in unexpected ways. And although photons have no mass at all, they can still exert a subtle pressure capable of pushing objects through space. As we continue our quiet journey through the quantum world, we now turn our attention to one of the most familiar forms of energy in the universe, light. Every day, sunlight warms the surface of our planet. Lamps illuminate our homes, and distant stars send their faint glow across the vastness of space. Light appears effortless and weightless, moving at incredible speed through the universe. Yet beneath its gentle brightness lies a surprising property. Light can push. At first, this idea may sound strange. After all, light has no mass. Photons, the particles that make up light, are completely weightless. Unlike atoms or electrons, they do not possess rest mass. But despite having no mass, photons carry both energy and momentum. And whenever momentum strikes a surface, it can produce a force. This phenomenon is known as radiation pressure. Although the pressure from ordinary light is extremely small, it is very real. When photons collide with an object, they transfer a tiny amount of momentum to that surface. If enough photons strike an object, the cumulative effect can create a measurable push. Scientists first confirmed the existence of radiation pressure in delicate laboratory experiments more than a century ago. Sensitive instruments were able to detect the faint force produced by beams of light reflecting from small mirrors.
The force was incredibly weak, but it matched the predictions of electromagnetic theory perfectly. In everyday life, the effect of radiation pressure is usually far too small to notice. Yet in the near vacuum of space, where there is almost no friction, even a gentle push can gradually produce significant motion. Because of this, engineers have proposed an elegant method of space travel known as the solar sail. A solar sail is a large, lightweight reflective surface that spreads out like a giant mirror in space. When sunlight strikes the sail, the photons reflect away, transferring a tiny amount of momentum to the spacecraft. Over time, this continuous pressure can slowly accelerate the craft without using fuel. Although the acceleration is small, the effect never stops as long as sunlight continues to strike the sail. Several experimental spacecraft have already demonstrated this concept successfully. These missions show that light itself can become a form of propulsion, gently pushing spacecraft through the silent darkness between planets. Radiation pressure also plays a role in astrophysics. Around young stars, intense light can push gas and dust outward, shaping the formation of planetary systems. In some extreme cosmic environments, radiation pressure can even oppose the force of gravity, influencing the structure of massive stars. In this way, the momentum carried by photons contributes to the dynamic balance of the universe. The idea that weightless light can move matter reminds us once again that the quantum world often defies our expectations. Even the simplest phenomena can hide deeper layers of subtle physics. But photons reveal yet another fascinating truth about nature. Because the particles of light that push objects through space are themselves not solid objects at all. They are tiny vibrations of an invisible field that fills the entire universe.
As our exploration of the quantum world continues, we begin to see that even particles like photons are not truly independent objects drifting through empty space. Instead, they are better understood as tiny vibrations in deeper structures that fill the universe. These structures are known as quantum fields. According to modern physics, every type of particle corresponds to its own field that exists everywhere in space. The electromagnetic field, for example, fills the entire universe. Whenever this field vibrates in a particular way, we observe the vibration as a photon. In other words, a photon is not a little bead of light traveling through emptiness. It is a small ripple moving through the electromagnetic field. This idea may seem abstract, but it becomes easier to imagine if we think again of the surface of water. When a stone drops into a pond, ripples spread outward across the surface. The ripples are not objects separate from the water. They are patterns of motion within the water itself. Particles behave in a similar way. They are patterns of energy moving through invisible fields that stretch across space. Every electron is a vibration of the electron field. Every quark arises from the quark field. Even the particles responsible for nuclear forces emerge from their own corresponding quantum fields. Together, these fields create the fundamental structure of the universe. They exist everywhere, even in places where no particles are present. When the fields remain perfectly calm, we perceive empty space. But when energy excites a field, a particle appears. This framework helps explain why particles can be created or destroyed in high-energy environments. When enough energy is added to a field, new vibrations can form, briefly appearing as particles before transforming into other forms of energy again. In particle accelerators, scientists observe this process regularly. When particles collide at enormous speeds, the energy of the collision excites various quantum fields, producing showers of new particles that quickly decay into other particles. These fleeting creations reveal the hidden layers of fields underlying reality. One particularly intriguing example is the gluon field, which binds quarks together inside protons and neutrons. The strength of this field is responsible for holding atomic nuclei together, making matter stable. Without it, the atoms that form stars, planets, and living organisms would fall apart. Even the masses of many particles arise from interactions between fields. The Higgs field, which we discussed earlier, permeates all of space. As particles move through it, they interact with the field and acquire mass. In this sense, mass itself emerges from the properties of an invisible field that surrounds us at every moment. The more scientists study these quantum fields, the more they appear to form the true foundation of physical reality. Particles become temporary ripples, fleeting disturbances in an underlying sea of energy. The solid objects we experience every day are actually vast collections of these microscopic vibrations interacting in stable patterns. And when physicists examine these patterns closely, they sometimes discover states of matter that behave in astonishing ways. One particularly remarkable example occurs when particles gather together and begin acting as a single quantum system.
As scientists explored the behavior of quantum particles more deeply, they began to notice that under certain conditions, groups of particles could begin acting together in a very unusual way. Instead of behaving as separate individuals, many particles could merge into a single shared quantum state. One of the most remarkable examples of this phenomenon is called a Bose-Einstein condensate. This strange state of matter was first predicted in the 1920s by two physicists, Satyendra Nath Bose and Albert Einstein. They realized that particles known as bosons could sometimes occupy the exact same quantum state if the conditions were right. But those conditions are extremely delicate. To observe this effect, scientists must cool certain gases to temperatures only a tiny fraction above absolute zero. At these incredibly low temperatures, the atom's motion slows almost to a complete halt. When this happens, the atoms begin to lose their individual identities. Instead of moving independently, they overlap and combine into a single large quantum wave. Thousands or even millions of atoms can behave as though they are one giant particle. In this state, the entire collection of atoms is described by a single shared wave function. The result is a new form of matter with extraordinary properties. Bose-Einstein condensates were first created in laboratories in 1995 using extremely cold clouds of rubidium atoms. The achievement required advanced cooling techniques involving lasers and magnetic traps. When the atoms finally reached the required temperature, something remarkable occurred. Instead of remaining as separate particles, the atoms merged into a unified quantum state that spread across the entire cloud.
Scientists could observe the condensate behaving like a single coherent wave of matter. The discovery opened a new window into the quantum world. In this unusual state, matter behaves in ways that normally occur only with light waves. The atoms can interfere with one another, producing wave-like patterns similar to those seen in the double-slit experiment. Because the atoms share the same quantum state, their motions become synchronized. The entire system moves together as one coordinated entity. This allows researchers to study quantum phenomena on a scale large enough to observe directly with specialized instruments. Bose-Einstein condensates have since become powerful tools for exploring the foundations of quantum physics. Scientists use them to study superfluidity, quantum vortices, and other exotic behaviors that reveal how particles interact at the deepest levels of nature. Although these condensates exist only under extremely cold conditions, they demonstrate something profound. The strange rules of quantum mechanics do not disappear when many particles gather together. Instead, under the right circumstances, those rules can become even more visible. The collective behavior of particles can produce entirely new states of matter. And Bose-Einstein condensates are only one example. Another remarkable phenomenon appears when certain materials conduct electricity with absolutely no resistance. In these systems, quantum particles again begin working together as a single coherent whole. This effect is known as superconductivity, and it reveals yet another surprising consequence of the quantum laws that shape our universe.
As we continue our quiet exploration of the quantum world, we encounter another remarkable phenomenon that reveals how quantum behavior can shape the properties of matter on a much larger scale. This phenomenon is called superconductivity. In ordinary materials, electricity moves through a conductor as electrons drift through the atomic structure of the metal. As these electrons travel, they frequently collide with atoms in the material. These collisions create resistance, which converts some electrical energy into heat. This is why electrical wires warm slightly when current flows through them. But in certain materials, when the temperature becomes extremely low, something extraordinary happens. The electrical resistance suddenly disappears. When a material enters the superconducting state, electrons are able to move through it without losing energy. Electric current can flow indefinitely without slowing down or producing heat. The motion becomes perfectly smooth, like water flowing through a frictionless channel. This effect was first discovered in 1911 by the Dutch physicist Heike Kamerlingh-Onnes while studying the electrical properties of mercury at very low temperatures. As the mercury cooled, its resistance steadily decreased. Then, at a critical temperature, the resistance abruptly dropped to zero. The discovery astonished scientists. At first, no one understood why this dramatic transition occurred. The explanation would not emerge until decades later, when physicists began applying quantum ideas to the behavior of electrons inside materials. They discovered that under extremely cold conditions, electrons can form special pairs known as Cooper pairs. Normally, electrons repel one another because they carry the same electric charge, but within certain materials at very low temperatures, subtle interactions with the atomic lattice allow electrons to pair up. Once paired, these electrons begin behaving as a unified quantum system. Instead of scattering randomly through the material, the Cooper pairs move together in a coordinated wave-like pattern. Because the pairs act collectively, they can flow through the material without being scattered by imperfections in the atomic structure. The result is a current that travels without resistance. Superconductors also display another striking property. When placed in a magnetic field, they can expel the magnetic field entirely from their interior. This effect is known as the Meissner effect. As a result, superconducting materials can cause magnets to float above them in stable levitation. In laboratory demonstrations, small magnets hover silently above superconducting surfaces, suspended by invisible quantum forces. These properties make superconductors extremely valuable for technology. They are used in powerful medical imaging systems such as MRI machines, where strong magnetic fields are required. They also play a role in particle accelerators and experimental fusion reactors. Researchers are searching for materials that can exhibit superconductivity at higher temperatures, which could revolutionize power transmission by allowing electricity to travel across long distances without energy loss. The phenomenon reminds us that quantum mechanics does not only govern the tiny world of atoms and particles. Under the right conditions, quantum behavior can shape the properties of entire materials. And when scientists continue exploring these quantum systems, they begin to uncover possibilities for technologies that may transform the way information moves across the world.
As the strange connections of quantum mechanics became clearer, scientists began to imagine new ways these principles could reshape the way information moves through the world. One of the most exciting possibilities is known as quantum communication. In traditional communication systems, information travels as electrical signals through wires or as light pulses through optical fibers. These signals can be copied, amplified, and sometimes intercepted without the sender or receiver ever knowing. But the quantum world behaves very differently. One of the most important rules of quantum mechanics is that measuring a quantum state changes it. This simple fact creates a remarkable opportunity for secure communication. Imagine sending information using individual photons whose quantum properties encode data. These photons might carry information through properties such as polarization, which describes the direction in which their electromagnetic waves oscillate. When the photons travel from a sender to a receiver, the receiver measures their quantum states to recover the message. But if someone tries to intercept the photons along the way, they must measure them in order to read the information. And that measurement inevitably disturbs the quantum state. Because of this disturbance, the receiver would immediately detect unusual changes in the signal. This principle forms the basis of quantum key distribution, a method for sharing encryption keys with extraordinary security. Once two parties establish a secure quantum key, they can use it to encrypt messages that cannot be secretly copied or decoded by outsiders. Even the most powerful computer cannot bypass the laws of quantum physics. The security comes not from mathematical complexity, but from the fundamental behavior of nature itself. Researchers have already demonstrated quantum communication across optical fibers stretching for hundreds of kilometers. Experiments have also used satellites to transmit quantum signals between distant ground stations. One such satellite mission successfully distributed entangled photons between stations separated by more than 1,000 kilometers. These experiments suggest that a future quantum internet may one day connect laboratories, cities, and even continents. In such a network, quantum states could be transmitted securely between distant locations. Entanglement could link distant nodes, allowing quantum computers and sensors to share information in new ways.
However, building such networks remains technically challenging. Quantum states are extremely fragile. Interactions with the environment can easily destroy delicate quantum information. Even small disturbances from temperature changes or stray electromagnetic fields can cause the loss of quantum coherence. To overcome these challenges, scientists are developing special devices called quantum repeaters. These devices would help extend the range of quantum communication by restoring entanglement between distant network nodes. If these technologies continue to advance, quantum communication could transform fields ranging from cybersecurity to scientific research. It may allow data to be transmitted with levels of security that were once thought impossible. Yet, even as these technologies develop, researchers are uncovering deeper questions about the nature of quantum connections. Some physicists have begun wondering whether entanglement itself might play an even more fundamental role in the structure of the universe. In fact, there is a growing idea that space and time themselves might somehow emerge from the hidden web of quantum connections.
As physicists explored the strange connections created by quantum entanglement, a bold idea slowly began to take shape. Some researchers started to wonder whether these invisible quantum links might be connected to something even more fundamental: the structure of space and time itself. In everyday experience, space appears as a vast stage on which events unfold. Distances separate objects, and time steadily carries the universe forward from one moment to the next. But modern physics suggests that space and time may not be fundamental ingredients of reality. Instead, they might emerge from deeper structures hidden within the quantum world. This possibility arises from attempts to unify two great theories of modern science. One is quantum mechanics, which describes the behavior of particles and fields at the smallest scales. The other is general relativity, Einstein's theory describing gravity and the large-scale structure of space-time. Each theory has been tested with extraordinary success, yet they are built on very different mathematical frameworks, and combining them into a single unified theory has proven extremely difficult. In recent years, some theoretical physicists have begun exploring the possibility that entanglement may provide the missing link. In this view, the geometry of space could arise from patterns of quantum entanglement connecting microscopic systems. The idea suggests that regions of space that appear close together may simply be areas where quantum systems share strong entanglement. Regions that appear far apart may share weaker connections. In other words, the fabric of space might be woven from networks of quantum information. One of the most intriguing hints supporting this idea comes from a concept known as the holographic principle. This principle suggests that the information describing a region of space may actually be encoded on its boundary, much like a hologram that stores a three-dimensional image on a two-dimensional surface. Within certain theoretical models, scientists have discovered mathematical relationships showing that the structure of space-time can emerge from patterns of entanglement in lower dimensional systems. Another fascinating proposal connects entanglement with tiny structures known as wormholes. Some physicists have suggested that entangled particles may be related to microscopic wormholes linking distant regions of space. Although these wormholes would be far too small to travel through, the idea hints at a deep relationship between geometry and quantum information. While these concepts remain highly theoretical, they offer a glimpse into a possible future understanding of the universe.
Instead of viewing space as an empty container holding matter and energy, we might come to see it as a network of relationships formed by quantum connections. The distances we perceive could emerge from patterns of entanglement. The flow of time might arise from changes in the structure of those connections. If this picture turns out to be correct, it would mean that the familiar world around us grows out of deeper layers of quantum information. Reality itself could be built from relationships rather than objects. Although much remains unknown, these ideas remind us how much of the universe still waits to be understood. And as scientists continue exploring these connections, they are discovering that entanglement may be far more common than we once imagined. In fact, the entire universe may be quietly woven together by countless quantum links.
As the idea of quantum entanglement expanded, many physicists began to look at the universe in a new and surprising way. Instead of seeing reality as a collection of separate objects scattered across empty space, they started to imagine it as an intricate web of relationships. In this picture, particles are not completely independent things. They are connected through countless interactions that have taken place throughout the history of the universe. Every time two particles interact, there is a possibility that they become entangled, even if only briefly. Over time, these interactions form a vast network of quantum connections. Most of these links fade quickly as particles interact with their surroundings. The delicate correlations of entanglement are easily disrupted by environmental noise, temperature, and other influences. Yet new connections are constantly forming as particles collide, scatter, and exchange energy. In this sense, the universe is continuously weaving and reweaving a subtle fabric of relationships. Some physicists have suggested that the early universe, shortly after the Big Bang, may have been filled with enormous amounts of entanglement. In those early moments, matter and energy were packed together at incredibly high densities and temperatures. Particles interacted constantly, creating a dense web of quantum connections. As the universe expanded and cooled, many of those connections faded, yet traces of the early entanglement may still linger within the structure of the cosmos. In modern laboratories, scientists have demonstrated that entanglement can persist over surprisingly large distances under carefully controlled conditions. Photons have been entangled across optical fibers stretching for many kilometers. In other experiments, entangled particles have been exchanged between ground stations and orbiting satellites. These achievements suggest that quantum connections can survive across vast distances when protected from disturbances. The possibility that entanglement exists throughout the universe raises fascinating questions. Could distant regions of space still share subtle quantum relationships originating from ancient interactions? Might the large-scale structure of the cosmos carry faint imprints of quantum connections formed billions of years ago? While these ideas remain speculative, they highlight how deeply quantum physics reaches into our understanding of reality. Even phenomena that seem purely cosmic may have roots in the delicate behavior of microscopic particles. This growing awareness has inspired new areas of research exploring how quantum information might influence cosmology and gravitational physics. Scientists are now studying whether the distribution of matter in the universe could be related to patterns of quantum fluctuations that occurred during the earliest moments of cosmic history. If so, the galaxies scattered across the sky might ultimately trace their origins back to tiny quantum ripples that existed long before stars were born. The thought is both humbling and beautiful. the same quantum rules that govern the smallest particles may also shape the largest structures in existence. And yet, despite all these discoveries, the quantum world still contains mysteries that remain unsolved. Even something as familiar as an electron continues to challenge our understanding of what a particle truly is. Because in the quantum universe, the simplest objects often reveal the deepest questions. As our journey through the quantum world continues, it is remarkable to realize that even the simplest particles still hold deep mysteries. One of the most familiar examples is the electron. Electrons are among the basic building blocks of matter. They orbit atomic nuclei, create chemical bonds, and allow electricity to flow through metals and circuits. Every technological device around us depends on the behavior of electrons moving through materials. Yet, despite their importance, electrons remain strangely difficult to picture. Experiments suggest that an electron behaves as though it has no internal structure. When scientists probe it with extremely high-energy collisions, they find no evidence that it contains smaller components. It appears to be a fundamental particle. At the same time, the electron does not behave like a tiny solid sphere. In many situations, it behaves more like a spread-out wave of probability. Its position is not fixed until a measurement occurs. Instead, it occupies a region of space described by its wave function. This wave-like description explains why electrons in atoms form the soft probability clouds we discussed earlier. These clouds are not simply mathematical tools, they represent real physical behavior that determines how atoms interact with one another. The arrangement of electrons around atomic nuclei controls the structure of molecules, the properties of materials, and the chemistry that makes life possible. Yet the deeper nature of the electron remains puzzling. Is it truly a point-like particle with no size at all? Or is it better understood as a vibration of the underlying electron field that fills space? Quantum field theory suggests the latter interpretation. In that view, the electron is not an object in the usual sense. It is a localized excitation of a field that extends throughout the universe. Wherever the field vibrates in a particular way, an electron appears. But the vibration is not perfectly stable. The electron constantly interacts with other quantum fields around it. Virtual particles briefly appear and disappear near it, subtly influencing its behavior. These interactions slightly modify the electron's properties in ways that can be measured with extraordinary precision. In fact, the theoretical predictions describing the electron's magnetic properties agree with experimental measurements to an astonishing number of decimal places. Few scientific theories have ever achieved such accuracy. And yet, even with this success, the deeper meaning of these quantum fields remains an open question. Why do these fields exist? Why do they possess the particular properties we observe? And why does the universe contain exactly the particles that it does? These questions reach beyond the boundaries of current scientific understanding. Physicists continue searching for deeper theories that might reveal the origins of the quantum fields themselves. Some proposals suggest that particles may arise from even more fundamental structures, such as vibrating strings or deeper layers of quantum geometry. While these ideas are still being explored, they remind us that the journey of discovery is far from complete. Each answer we uncover opens the door to new questions,
And sometimes the universe surprises us with phenomena that appear almost magical. Because in certain quantum systems, particles can flow in ways that seem to defy friction and resistance entirely. These extraordinary behaviors reveal yet another hidden side of the quantum world.
As scientists continued exploring the strange behaviors that emerge in the quantum world, they discovered another remarkable phenomenon that seems almost magical when first encountered. It is called superfluidity. In everyday life, liquids experience friction when they flow. Water moving through a pipe encounters resistance from the walls and from the molecules rubbing against one another. Over time, this friction slows the flow and converts some of the energy into heat. But under extremely cold conditions, certain liquids begin to behave in a completely different way. They can flow with no internal friction at all. This extraordinary state is known as a superfluid. The phenomenon was first observed in liquid helium in the early 20th century. When helium is cooled to temperatures just a few degrees above absolute zero, it suddenly undergoes a dramatic transformation. The liquid begins to flow without resistance. If placed inside a container, superfluid helium can climb up the walls and spill over the edge as though gravity itself has become less important. It forms thin films that creep along surfaces and pass through extremely tiny openings that ordinary liquids cannot enter. The fluid moves in smooth, continuous motion without losing energy. This strange behavior arises from quantum mechanics. At such extremely low temperatures, the atoms in the liquid slow down enough that their quantum wave functions begin to overlap. Instead of behaving like separate particles, the atoms merge into a shared quantum state. Much like the Bose-Einstein condensates we discussed earlier, the entire collection of atoms begins behaving as a single coordinated wave. Because the particles move together in this unified state, they can flow without the scattering that normally produces friction. The motion becomes perfectly smooth. Superfluids also exhibit other unusual properties. When stirred, they can form tiny whirlpools called quantized vortices. Unlike the swirling patterns seen in ordinary fluids, these vortices can only exist in discrete amounts determined by quantum rules. The circulation of the fluid occurs in precise steps rather than continuous values. These delicate structures reveal the hidden quantum order within the fluid. Scientists study superfluids to explore how quantum mechanics behaves on larger scales, where its effects can be observed more directly. Superfluidity is not limited to helium. Similar behavior appears in ultra-cold gases, certain atomic systems, and even in the dense interiors of neutron stars. In those extreme cosmic environments, matter may form enormous superfluid regions deep within the star's interior. These discoveries remind us that quantum mechanics is not confined to tiny laboratory experiments. Under the right conditions, quantum effects can shape the behavior of entire fluids, materials, and astronomical objects. The strange rules governing particles and waves quietly influence systems across an astonishing range of scales. And as scientists continue studying these quantum systems, they are beginning to uncover connections between quantum physics and some of the largest mysteries in the universe. Because the same principles that govern particles in laboratories may also help explain how the universe itself began.
As we move further along this quiet journey through the quantum world, we begin to notice something remarkable. The strange rules that govern tiny particles may also have shaped the largest structures in the universe. To understand this connection, we must travel back to the earliest moments after the birth of the cosmos. According to modern cosmology, the universe began with an event we call the Big Bang. In the first fractions of a second after this event, the universe was unimaginably hot and dense. Space itself expanded rapidly, stretching tiny fluctuations into larger structures. These fluctuations were not ordinary disturbances. They were quantum fluctuations. In the earliest universe, energy fields filled all of space, just as quantum field theory predicts. Because of the uncertainty principle, these fields could never remain perfectly calm. Tiny variations in energy constantly appeared and disappeared within them. Normally, these fluctuations are incredibly small and short-lived. But during a brief period known as cosmic inflation, the universe expanded at an astonishing rate. Space itself stretched faster than light could travel. This rapid expansion magnified the tiny quantum fluctuations, spreading them across enormous distances. What were once microscopic ripples became the seeds of cosmic structure. Over billions of years, gravity gradually amplified these small differences in density. Regions with slightly more matter attracted more material, slowly forming the first galaxies and clusters of galaxies. In this way, the vast cosmic web of stars and galaxies that fills the universe today may trace its origins back to tiny quantum ripples that existed in the earliest moments of time. When astronomers observe the cosmic microwave background, the faint glow left behind from the early universe, they see subtle patterns that match these predictions. The tiny variations in temperature across the sky correspond to the ancient fluctuations that were stretched by cosmic inflation. These patterns serve as a kind of fossil record of the universe's earliest quantum activity. The idea that galaxies, stars, and planets ultimately grew from microscopic quantum fluctuations is one of the most profound insights of modern science. It reveals that the smallest laws of nature helped shape the largest structures in existence. The same principles that govern electrons inside atoms also influenced the formation of galaxies containing billions of stars. This deep connection between the very small and the very large reminds us how unified the universe truly is. Quantum physics may seem strange and abstract, but its influence reaches far beyond the tiny world of particles. It played a role in shaping the cosmos itself. And as scientists continue studying these connections, they are beginning to ask even deeper questions. Could the entire universe itself be described as a vast quantum system? Might the fabric of space, time, and matter all arise from deeper quantum information processes? While these ideas remain the subject of ongoing research, they suggest that the universe may be even more mysterious than we have imagined. And yet, within all this complexity, there is also a quiet beauty, a sense that the universe unfolds according to subtle patterns written into the fabric of reality itself. As we gently approach the end of this journey through the quantum world, we arrive at a question that has fascinated scientists for decades. What if the entire universe itself behaves like a quantum system? In the experiments we have discussed so far, quantum effects appear in small systems, photons, electrons, atoms, and carefully controlled laboratory environments. But the same mathematical laws apply everywhere in nature. Nothing in the equations of quantum mechanics says that the rules should stop at a particular size. In principle, the entire cosmos could follow the same quantum principles. This idea leads physicists to explore a field known as quantum cosmology. Instead of studying individual particles, quantum cosmology attempts to describe the whole universe using quantum theory. The goal is to understand how space, time, and matter behaved during the earliest moments after the Big Bang. At that time, the universe was incredibly small and dense. Under such extreme conditions, quantum mechanics and gravity would have interacted in ways that modern theories still struggle to fully explain. Some scientists propose that the universe itself may have existed in a kind of quantum superposition in its earliest state. Different possible configurations of space and matter could have existed simultaneously, described by a cosmic wave function. As the universe expanded and cooled, interactions may have gradually selected the particular version of reality that we experience today. In this view, the classical universe we observe may have emerged from deeper quantum possibilities. Another intriguing idea suggests that information may play a fundamental role in the structure of reality. According to this perspective, the fundamental processes of nature may resemble computations occurring within the fabric of space-time itself. Particles interact, exchange information, and evolve according to the rules encoded in quantum theory. Although these ideas remain theoretical, they reflect a growing shift in how scientists think about the universe. Rather than seeing reality as a collection of solid objects moving through empty space, many physicists now imagine the universe as a dynamic network of relationships, information, and interactions. The objects we perceive, atoms, stars, planets, may simply be stable patterns within that deeper network. This view does not diminish the wonder of the universe. If anything, it deepens it, because it suggests that beneath the familiar world lies a rich and subtle structure filled with connections we are only beginning to understand. The more we study quantum physics, the more it invites us to rethink our assumptions about what reality truly is. Perhaps the universe is not made of things. Perhaps it is made of relationships. And with that thought, we arrive at a quiet moment of reflection, a reminder that even after more than a century of studying quantum mechanics, the universe continues to reveal new mysteries waiting to be explored.
And so, as our journey through the strange and gentle landscape of quantum physics slowly comes to a close, we return to the world around us. The room you are in feels solid. The ground beneath you feels steady. Time continues moving quietly forward, just as it always has. Yet now, perhaps, the universe feels just a little more mysterious. Because beneath the familiar surface of everyday life
lies an extraordinary hidden layer of reality. A world where particles behave like waves, where possibilities can exist side by side until a measurement brings one of them into view, where two particles separated by enormous distances can still share a quiet connection, and where empty space itself is never truly empty. These discoveries remind us that the universe is far more subtle and beautiful than it first appears. For centuries, humans imagined the cosmos as a giant mechanical system, predictable and precise, like a perfectly constructed clock. Quantum physics revealed something softer. Reality is not built from rigid certainty. Instead, it is shaped by probabilities, relationships, and delicate interactions unfolding beneath the surface. Even the objects that feel most solid are made almost entirely of empty space, held together by invisible quantum forces and fields. The atoms forming your body were once forged inside ancient stars. The electrons moving within those atoms follow the same quantum rules that guide the light from distant galaxies. In this sense, the same laws that govern the smallest particles also connect us to the vastness of the cosmos. The universe is not divided between the very small and the very large. It is a single, continuous story written in the language of physics. And despite everything we have learned, the story is far from complete. Physicists continue searching for deeper theories that might unite quantum mechanics with gravity and reveal the ultimate structure of space-time. New experiments probe the boundaries of quantum behavior, exploring how far these strange effects extend into the macroscopic world. Some researchers are even beginning to wonder whether consciousness itself might somehow relate to the fundamental processes of quantum reality. Whether these ideas prove correct or not, one thing is certain. The universe still holds countless secrets waiting to be discovered. Every generation of scientists uncovers new layers of understanding, and with each discovery, the mystery grows richer rather than smaller. Perhaps that is one of the most beautiful aspects of science. It does not remove wonder from the universe. Instead, it deepens it. So tonight, as the world grows quiet and the mind begins to drift towards sleep, you might imagine the invisible quantum fields quietly vibrating throughout the cosmos. Particles appearing and disappearing. Possibilities gently unfolding into reality. All of it happening silently beneath the calm surface of the world we see. A hidden symphony of nature playing endlessly in the smallest corners of existence. And somewhere within that vast and subtle harmony, we are also part of that same unfolding universe.